Okay, this is just a quick introductory to nuclear chemistry, and we're only going to spend 1 or 2 days on this. There's a lot you could cover on this, but we're just going to give you the quick basics on this particular topic. Just so we have an understanding of what nuclear reactions are and basically what the topic of the chapter is. Nuclear reactions involve the change of an atom's nucleus. So the change of an atom's nucleus right here, an atom's nucleus. And the next thing you have to understand or know is a terminology called a radioisotope. It's an isotope of an element that is unstable or radioactive. It can be either unstable or radioactive. Now remember, we talked about isotopes before being the same chemical, having the same number of protons, so example chlorine, but a different number of neutrons. So the atomic mass is different, but the number of protons is the same. So we have carbon 14, carbon 12, carbon 13, oxygen 18, oxygen 16. So that is an isotope, and a radioisotope is one of those that is unstable. And the stability of an isotope is based on the ratio of the neutrons and protons in the nucleus. If we have too many or too few neutrons, we will cause an isotope to be unstable. We talked in the other slide about having the stability of an atom based on a couple of factors, but the number of neutrons versus the number of protons. In this case, you can see that when we have the protons and the neutrons equal, we get this line right here, and I'm drawing a line right up the thing here. And that's a slope of 1, so that means that n is going to be equal to z. So 60 here equals to 60 here, and if you go to the line, you can see that. Now, when you have the early elements on the periodic table, up to about calcium, which has an atomic number of 20, you can see that it's fairly religious about following the n equals z rule, where you have 1 proton for every 1 neutron in the nucleus. As you get close to 20, or when you start going further up the periodic table or into the periodic table, you can see now that the band of stability, in other words, where the atoms are stable, the ratio of the number of neutrons to the number of protons is biased to the neutron side. In other words, there are more neutrons than there are protons in elements that are greater than calcium. And as you can see, as you get up to the gold area, which is at 79, let's just draw a rough thing here. We should be here. We should have a 1-to-1, but we're almost always almost 115 to 120. So an increase of over 35 more neutrons than there are for the number of protons. So quite a big difference. And so that's the trend that you're going to see, but we're going to call this band stability. And we're going to use this later on when we see how these elements that are above 92 decompose. Now remember, according to the other slide and some of the other things we've talked about, we need to identify which one of those are radioactive elements. All elements that have an atomic number of greater than 83 are going to be radioactive. They have no stable isotopes. In other words, they are going to decay at some level. These elements will naturally decay, as I just mentioned, to form more stable isotopes or elements in the case. Uranium is the last naturally occurring element in the periodic table. Everything above uranium or having an atomic number greater than 92 are man-made. Some of these elements stick around for a little while. Some of them elements are very, very short-lived. and some elements have only been made in very minor microgram quantities ever. But they were around, and they did exist for at some finite level of time. When elements radioactively decay, they're going to give off some type of emissions to get rid of some of their particles as they decay into more stable isotopes. And so let's look at what those are right now. The first one we're going to call, and the type of decay is going to be called alpha decay. So there's my alpha decay, and it's when we emit a helium nucleus. Not a helium atom, a helium nucleus. So there are no electrons being emitted. Remember, this is coming from the nucleus, so the nucleus is emitting a helium nucleus. So we have uranium-238 here, decaying into thorium-234 and giving off a alpha particle, which is what we call our helium nucleus. And note one thing, that the 238 here equals 234 plus 4, and that 92 equals 90 plus 2. Remember, we cut down the arrow here to equal. This side has to equal this side. Our beta decay is the emission of an electron during the conversion of a neutron to a proton. So we are now changing the inner nucleus structure by converting one of the neutrons into a proton, and the way we do that is we lose a negative charge. And how does that happen? So let's say here we have carbon 14. We know that carbon has an atomic number of 6, so there are 8 neutrons available. So there's 8 neutrons here. And in this side, we have nitrogen 14. Notice that the 14s are the same. We haven't changed anything as far as the atomic mass, but now we've gone up a level as far as the number of protons. So now we have, as you know, we have 7 protons here, and here we had 6 protons. And now over here we have 7 neutrons. So we've taken one of the neutrons here and we've converted it into a proton here. And so therefore there's an increase this way and a decrease this way for the number of neutrons. But the overall, the mass stays the same, right? So we haven't changed anything as far as the mass. We've just changed the number of protons versus neutrons in each one of these. And then when we do that, we make sure that we have to balance our charge now, because now we have protons here. If we add another proton, we increase the positive charge, so we have to take that away by emitting an electron. And then gamma rays are just high energy rays. They don't have any charge, they don't have anything, they're not particles. And the last one we talked about was the emission of a neutron, and you could see that over here. And you're not going to see that much in this chapter, but if you go on in science, you may see this written like this, where n is the neutron, and it doesn't have a charge, so it's 0, and so that's what it would be written by. Now let me just make that a little bit cleaner, so that it's actually not written on a slant. It's actually written something like this, right? And very similar to something like this, except now we have an n, and we have a 1 on the top and a 0 on the bottom, right? Let's talk now about the characteristics of each type of the radiation. On this side of the slide, I'm going to list the symbol. So here we go. This is the property, and here's my symbol: charge, mass, penetrating power, and shielding. I'll get to all these in a minute. And then we have our alpha particle, or alpha decay, beta particle, or beta decay, and then our gamma particle, gamma decay. Let's just quickly go through each one by the columns by. So our alpha particle, as we know, is going to be represented by a helium nucleus, which we're going to call 4. It has 4 total units in it, 4 atomic mass units, 2 protons, 2 neutrons. It has atomic number of 2. And then here's my chemical symbol for helium. or we're going to list it just as an alpha, just as the Greek letter alpha. And since it has 2 protons and no electrons, it's going to be +2. Our atomic mass, as already, is 4. It has this thing called penetrating power, which is basically how strong it is as far as a radiation thing for penetrating a surface. And in this case, it's very low. Most of the time, it can be shielded with just paper or thin clothing. All right. Our next one is beta. It's our beta particle, and basically, remember that was an electron. And we also talked about if it could be a positron, which is a negative electron, and we'll talk about that briefly, but not too much. So a beta is going to be represented by this symbol or this symbol, of this series of symbols, and beta. Remember, it's an electron, so it has a -1 charge. It really doesn't have any mass, but for all intents and purposes, it's about 1/2000th of a mass unit. It does have some penetrating power. Remember that when Rutherford did his experiment, he was he's putting a column of electrons through with a very thin foil. So some foil will stop most of the electrons, but if the foil is very thin, some of it will go through. So you need to have a thickness level that is appropriate for the energy of the electrons. And so a thin metal foil, like aluminum foils, should be fine. And our last one is gamma. Gamma radiation has no charge, no mass. All right, so no mass, no charge. There's no mass, no charge. It does, however, penetrate quite highly. It's very high energy, so it's going to go very deep in penetration. Gamma rays are very damaging to humans, and therefore the only thing that really stops it well is heavy metal like lead or very thick concrete. And the other one that we talked about real quick, what I told you about the neutron. The neutron would be slightly less heavy than the alpha particle here. So it would have high-low, I guess, or low moderate penetration power. So it would be in this range here. And, it would be, it does have some mass. It doesn't have any charge. So it would be somewhere around here as far as penetrating power. Writing nuclear equations to describe what is happening during a nuclear decay reaction is quite simple. So we know that the subatomic particles cannot disappear. We must maintain the mass of the numbers of both the protons and the atomic mass throughout the reaction, or throughout the nuclear decay reaction. So, and then we have a couple other terms here. Let's just call them here. We have this thing called the parent, right? The parent, and the parent always is going to give a daughter, have a daughter, and then another offspring here, which we're going to call our decay particle or a decay species. So our daughter is going to be some other type of element, and then our decay species is going to be, you can think of it like a dog or something like that, but it's decay species. So we have a parent, gives birth to a daughter, and then some other species, right? And this is our decay species. And remember, the atomic mass numbers must add up. So if we split down the arrow here, that's our equal sign. 238 equals 234 plus 4. And then on the bottom side, as far as our atomic number, 92 must equal 90 plus 2. So that we have 92 on this side, 92 on this side, 238 on the top, 238 on the top. So everything checks out. Now this slide is in your slide deck, and it's one of these ones where you can go through, and when you hit return enough times you can slowly fill in the results. But I've already printed them here, and this is mostly for educational purpose. So let's look at here what's happening. We have a species here, aluminum 25. Remember, we're always going to say it's aluminum 25 because if I say it's aluminum, we already know by definition that it has to have the 13 protons, but I need to tell you if it's an isotope or not. So normally this is aluminum 27. And what's going to happen here is aluminum 25 is going to undergo some radioactive decay by losing an electron and converting one of its neutrons into a proton to give me silicon 25. And we already know by silicon 25, we already know we have 14 protons. So one of the neutrons here is getting converted to a proton and the loss of the electron. So that's our beta decay mode. And the americium is spelled A-M-E-R-C-I-U-M, is going to undergo a alpha decay, where it's going to lose an alpha particle, which is our helium nucleus, and form neptunium. This is Neptune plus I-U-M, neptunium. And so if we add up the atomic masses here, we have 241. Remember, here's our equal sign, basically. And then 4 plus 237. And 95 equals 2 plus 93. And so this is our alpha decay. And the other two here, you can see from the math and how we set it up, that they're all going to equal the numbers on the left side, going to equal the sum of the numbers on the right side. All right. So if you're not understanding this concept, you should find me. If you're getting it, you can quickly move on to the next concept. What I would like you to do in this slide is the following. You are going to write down the two decay equations for the two scenarios that we have here. I'm going to ask you to stop the video, copy the information down, and then solve the equations using what I've written here. Now for actinium-230, you're going to have to look that up as far as what the atomic number is for that. Remember, the 230 is the atomic mass, not the atomic number, and the same thing with fluorine, right? So when you're ready, you're going to stop the video, copy the information down, do the decay equations as requested here. When you are finished and ready, start the video again, and I will give you the answers. So stop when you're ready. So now that you're back, we now can look at the answers that we have written. So if you looked up actinium, you would have found out that it has the atomic number of 89. And so you would write the chemical symbol for this, actinium-230, this way. I told you it's an alpha decay, so you have an alpha particle that you are generating, and to balance that out, you would list francium as your your daughter. Remember, this is our parent, and this is our daughter, and this is the decay particle that we're generating. And so in order for this to match up, we need to find what element was 87. That's francium, and then the top ones would match for the atomic mass. Again, the same concept is for fluorine here. We know that fluorine is atomic number of 9, and then when you do the math here, you have to find out that neon, which is the atomic number of 10, is going to give you the proper solution to this one. If you're still struggling with this, you should find me and we can go over this a little bit, but if you're getting this, that's pretty much the details that you're going to have to need, or the extent you're going to have to need. In terms of radioactive decay or nuclear decay, transmutation refers to the conversion of an atom of one element to the atom of another element. This can be either artificial or natural, and we'll talk a little bit about both in the next two slides. Artificial transmutation is accomplished by bombarding the nucleus of an atom with high energy particles, either other atoms, alpha particles, protons, or neutrons. We do these bombarding reactions in particle accelerators. Particle accelerators are very large units of high electromagnetic fields, and when we generate an electromagnetic field, we can accelerate charged particles down the field into a target that contains the material that we want to bombard. This is the only way we're able to use to create synthetic elements. And so what I'd like to do here is just show you how we are writing the artificial transmutation material for this creation of, let's call it element 118, element 118. And if we do that, and we do it with a calcium atom, and we bombard that into a californium atom, which is californium is right here. This is my californium. Here's my calcium. And if we look up californium, you know it's radioactive because it's greater than 83. It's also synthetically made because it's greater than 92. If we take this synthetically made material and bombard it with calcium, our goal is to get this large material here. We're going to call it element UUO. And remember, these top numbers have to match up to this, and these top numbers have to match up to this. And so that would be our process for making element 118 with californium and calcium. Distinguishing between natural and artificial transmutation is quite easy. The natural one has only one reactant. It is basically a decay, radioactive decay reaction. The artificial one has more than one reactant. In this case, we are probably bombarding two materials together to try and create another material, either by itself or a large material with some type of offspring, like an alpha particle or gamma particle, something like gamma rays or something like that. So combination of two materials to get, as far as reactants, was the artificial one. Natural is the one that only has one reactant. Okay, so now we've gone through this, what I'd like you to do is stop the video and work on the first worksheet, which has the writing the decay reactions and predicting what the products and reactants are. And when you're done that, you can start the video again and we'll go into the next concept. All right, so stop the video now, work on the worksheet that I gave you, the first worksheet, and then when you get done that, you can start the video again and go into the next concept. When we talk about half-life, we're referring to the decay rate of a radioactive substance. The decay rate is not dependent on anything like temperature, pressure, or concentration, unlike a chemical reaction, which most often or not is dependent on temperature, pressure, or concentration. Half-life is defined as the time it takes for half of the atoms in a given sample of an element to decay. So for half of the atoms to change from one state, their initial state, into a new state. The shorter the half-life, obviously, the less stable it is. Here are some nuclides that we have various types of half-lives for them, and their decay mode, and then their nuclide name. So on this column here, we have the chemical symbols for the nuclides. And notice that you don't see the full symbol here, you just see the atomic mass, because by giving you the chemical symbol, you should automatically know or be able to determine what the atomic number is. Here's my half-life column. This tells you how long it takes for half of the atoms to decay away from the original form. And then this is the mode of this decay. And then this is what we're going to call it as far as if you were writing it in a paper or something like that. Gold 198. There's my chemical symbol for gold. Here's my 198. Iron 53. There's my 53, and there's my iron. All right, so that's pretty much it for this chart. Occasionally, you'll see if you get into this a little bit further, you may see something that you haven't seen yet. Is this thing called a positron, this beta plus. The beta plus is basically a negative electron. Right? It's not electrons are negative. This is an electron that has a positive charge, which is kind of weird, but it doesn't have any mass. It has very little mass, like an electron, but it has a positive charge. All right. It's a little bit beyond the scope of this course, but I just want to make sure that if you saw this, it's not a typo. There is things called positrons. Half-life is not just indicative of radioactive decay. There's all kinds of things that deal with half-life. And it's basically, the general understanding is that half-life is when half of the material has been used up, and then half of the material has been used up. For radioactive decay, we can understand now and use this knowledge to help us understand things like how old a rock is or how old a skeleton is. Because if we can find trace elements in there that have radioactive properties, like carbon-14, and we know the half-life cycle of that, then we can estimate how old something is just by looking at how much material is remaining. So let's see what happens when we do this. To understand how this works, it's fairly straightforward. We're always going to have half of the material remaining that we started with after one full half-life cycle. So we're looking at this chart here. It's kind of confusing, but let's just see how it works. Every time that we decay one half-life, we decrease everything by half. If, on the other hand, I tell you that we have, let's say 10 grams of material, and I know the half-life is 3 days, how much material did I have 60 days ago, and we want to calculate what we started with, we are always going to be multiplying by a factor of 2. So we want to go from, do you see how much we're decaying? We're going to divide by 2, and if we want to understand how much we had from a certain amount, we're going to multiply by 2 for each half-life. So let's see how this works in a real scale. So forget about this chart for a second. Just kind of follow me on the bottom of the page here. I'm going to start out with exactly 100 grams of material. And for every 100 grams, I'm going to say that I want to go, how much do I have after each half-life? And let's say we'll go to 4 half-lives. So let's start off with the first one. So at half-life 0, we'll just put the 0 here, we have 100 grams. At the end of half-life 1, we have half of 100 grams. We have 50 grams. At the end of the next half-life, think of it starting like we're starting fresh at 50 grams, and we're just doing another half-life of that. So we have 2 half-lives total, but we have only 25 grams left. It's half of what this was, and this one is half of what this was. So now let's go to number 3. We have 3 half-lives we have done. So number 3, we're going to have 12.5 remaining of the 100 grams. And after the 4th half-life, we said we're going to do 4. We have 6.25 grams remaining. Okay? So notice what happens here. We were halving each time we did it, right? It's not like we'd started out with 50 and then we went to 40 and then 30 and whatever. We actually were halving each one, right? So how do we can we write this a different way? Well, sure, we can write this a different way. Let's try doing this way, right? The factor is that for every half-life, I'm going to decrease by half. So let's just write the general equation of 1/2. And we know for every half-life, I'm going to multiply it by a half. So we're going to do 1/2 of that and 1/2, and I have a half left over and a half left over, right? And if you look at this from a mathematical point of view, you're going to say, well, that's weird. I have 4 2's on the bottom. How can I better represent that? Well, you can do that easily. You're going to say that you have 2 raised to the n. And n is the number of times that you're going to multiply by 1/2. In other words, the number of half-lives that your cycles you're going through. So n equals half-life cycle. Okay? That's how simple it can be. And if you were trying to increase it, it's just the other way. Instead of dividing by half, let's go up here. It's just 2 times 2 times 2 times 2, or 2 to the nth. We're going up. If you wanted to find out, let's say I have 10 grams left, and I wanted to find out how much did I start with three half-life cycles ago, it would be 2 to the third times the amount you have left. Let's see how this works in the next couple of pages. Okay, so on the previous page, I gave you a couple of ways to do this. So again, I'm just going to quickly go through the first concept that we did. So remember, we're starting out with 40 grams, and I want to know how long is it going to take for me to get down to 101.25 grams. So I could do the old, let's divide it by half, let's divide it by half. And I also know here that my half-life is 12 years. So every time I go 12 years, I'm doing another half-life. So after my first half-life, which is 1, I've elapsed 12.3 years. And I have this much remaining, 1/2 of the remaining. All right. And then if I look at the half of that, that's 10, that's 2 half-lives. And the fraction I have remaining from the start is 1/4. Remember, it's now 10 divided by 40. Since that's my start, this is what I have now. So it's 10 divided by 40. All right. And so we can continue down. So that's the first 2 half-lives are completed, and we're only 10 grams. We've only got 10 grams left over. Now let's look at the next one. We've got down to another 3 here, and we've taken half of 10. That's 5. And that's now taken us 36.9 years, and we have 1/8 of the material left that we started with. And you can see if we go all the way down to 5, we get our 1.25. This is 61.5 years, and we have 1/32 of our material remaining. So now let's look at that from the other way real quick, just to show you what I mean by the other way. Okay, the other way is now, I remember I said that instead of dividing, you could say, well, we have 5 half-lives left, right? So we know this we don't know this column yet. We don't know this column yet, right? But we can take 1.25 grams, and we can take that and we can put that here, and we can say, well, we started out with 40 grams. And if you do the math here, you're going to find out that you're going to get the fraction that equals 1/32. Right? So it's going to be 1/2 to the n must equal 1/32. And if you find that out, you're going to find out that n to the 2 to the 5th is going to give me 32. Right? So you can solve it either way. One way is you'll get the answer, but you'll have to do a lot of dividing by 2. Or the other way is you can you can do this way first and get your decimal fraction converted to a fraction. It's either going to be, one of these. It's going to be 1/2, 4, 1/8, 1/16, 1/32, 1/64, etc., etc. And then convert that into one of these, and you can get the number here. Each way has its merits. There's no right way or wrong way. Some are easier to do than others, and it gets better to do it this way when you have a half in between one of these. Let's say you only had 7 grams left. Right, so now you can have to figure out how many half-lives that is, and this way lends itself better to that. All right, in this case, let's look at how much Fe61 will remain after 18 minutes, and I'm telling you that you have a half-life of 6 minutes. So we know that if we have 18 minutes, right? If we have 18 minutes, and we divide that number by 6 because that's the half-life, we have 18 minutes total, we get that we have 3 half-life cycles, right? So we know that we have 3 half-life cycles, and then so how much will remain? So you could say that we're going to have 1/2 times 1/2 of that times 1/2 of that is going to give me 1/8, right? Or you could have said 2 to the n, and n is 3, and that's going to give me 1/8. So 1/8 is how much is going to remain, and we can just take 1/8 and multiply it by 100 grams, and then we'll find out that we get 12.5 grams as our answer, right? And that's written right here too. So there's two ways you can got there fairly quickly. In this problem, I am asking for you to find out what is the half-life in number of days. But I'm giving you some information here that you need to understand how to do that. So I'm telling you in the first part of the problem that it took us 20 days to go from this number here, 120 kilograms of bismuth 210, down to 7.5 kilograms of bismuth 210. So let's see what that looks like in real life. So if I'm going to say how much do I have remaining, so I'm going to make 7.5 kilograms. That's what I'm remaining over what I started with, right? Kilograms. And if I do that math, you will find that you have in fraction form 1/16, right? Because I'm looking for the fraction remaining, right? And so let's see how we would have got there. Well, we need to understand how many half-lives that we went through to get to 1/16, and it's very common. It's very simple. The first one is going to be 1. Here's my second one. That gives me 2. Here's my third one. That's 3. And here's my fourth one. That's 4. Right? And they're always going to be multiples of 2, 4, 8, something like that. So half-life is going to be half of that, half here, half of that number, half of that number, another half of that number. Right? So it's basically 1 over 2n, and we now know that we have n is equal to 4. Right? So if we know that n is equal to 4, and we know that we've got 4 half cycles in 20 days, we now can be able to solve the problem. So it took us 20 days, and each half-life is 4. We had 4 half-lives in that 20 days, so we need to solve for x, and x equals 5 days per half-life. All right, it's that simple. Another example of how this could work is I'm asking you now for the percent of a sample of radioactive element whose half-life is 5 years will decay after 25 years. So what we're looking for is how much is going to be left after 5 years to further decay. And so we have 5 years, and we have 25 year total, and we have 5-year half-life. And we know we have 25 years and 5 years, so now we can do the simple math. We have 25 years, and we're dividing that by every 5 years we have a half-life of 5, so let's do that 5. So we go through 5 half-lives. Right? And we know the progression now, start by heart, right? For every half, so here's my first progression, half, then we go to a quarter, eighth, 16th, finally we were down into the 32nd. So we have 1/32 of the sample left over, and if you take 1/32 and do that into a decimal and then multiply by 100%, you get 3.1% remaining. So that's going to be left over after 25 years to further decay. Now, we're not always looking for how much stuff is going to be left. In carbon-14 or radioactive dating, we actually have a sample that has been decaying over time, and we want to find out how old something is by back calculating how many half-lives the material went through over time. So let's see how we could do that. So K42 has a half-life of 12 hours. At present, a given ore sample contains 34.2 milligrams of K42. How much did it contain yesterday at the same time? So we're actually going back in time. So let's see how we would work this one out. So I have 12 hours as my half-life, and a day is 24 hours. So in 24 hours, we've gone through 2 half-life cycles, right? So let's do that. So we've gone through 2 half-life cycles, and so here they are. A fraction remaining after 0 half-life cycles is 1. That's 100%. After the first one, we have a half left. And after the second one, we have a quarter left. So we have a quarter left of what we initially started with. So if we have a quarter left of what we initially started with, we need to know what quarter x is. X is our what we initial, right? Initial. And then now we know that equals 34.2, right? So this becomes a simple algebraic equation where you're going to multiply each side by 4 and isolate the x. And so now you're going to have 4 times 34.2 is going to give me 136.8 milligrams. All right, 136.8 milligrams. And that's how simple. So now we're working backwards, right? We know what we have now. We're trying to predict what we had in the beginning, or make the calculation we had in the beginning. And this is how carbon-14 dating is used. At this point in time, you're going to stop the video now and work on the half-life worksheet that I gave you. And what you don't finish either today, either worksheet, is going to be homework for the day we return for class. So stop the video now, work on the other worksheet, the half-life. When you're done, then you can resume the video. If not, you can resume the video at home and finish watching it. I will go over some of this tonight. Some of this the next time that we meet before the end of the year. So stop the video now, work on the worksheet, start it again when you're done, and move forward. Okay, the last two concepts for this chapter are basically talking about this term. You've heard them before, probably fission and fusion, nuclear fission and nuclear fusion, right? And they're basically opposite each other from a standpoint of what's going on. In fission, we are splitting a heavy nucleus to produce a lighter nuclei, well, the fissile, right? A heavy nucleus captures a neutron, forms two middleweight nuclei, one or more neutrons, and then a lot of energy. And the process is typically used in a nuclear power station. It's a controlled chain reaction, right? So if you add too much stuff, you're going to get a runaway reaction. You've heard of that before. If you don't add enough stuff, you're not going to get a lot of energy. So here's the cartoon of how it works, right? Let's just look at it. So we bombard a uranium-235 atom with a neutron. And that splits this atom into two smaller atoms, and those release more neutrons, which then attack another uranium-235 atom. And again, that splits. So it's a chain reaction. For every one of these we split, we get 3 more neutrons and such. And it continues down the line. And here's another cartoon here. So for every one of we got a neutron, uranium nuclei. The neutron hits the nuclei, breaks this apart. The neutron again goes to the next guy. This one goes to another person. And then we just keep going down the chain of it's a chain reaction, right? For every one we break, we make more things that we can then use more of those to break. So it's like almost like a geometric increase, right? Very high energy, a lot of energy comes out of it. So that's how your power plant works. So fusion is just basically opposite of fission, where in fission we are breaking things apart, in fusion we're bringing things together. And the goal is to take two lighter nuclei to produce a heavier nucleus fused together. We require a lot of energy to do this, right? And what we need the energy to do is to overcome the repulsive forces of the charges of the hydrogen nuclei, right? And in this case, the nuclei. So what we're going to do here is we're going to take two types of hydrogen. One is deuterium, where it has 1 proton, and it has 1 neutron. Normally, hydrogen doesn't have any neutrons, right? So here's my deuterium atom. And in the other case, tritium, we have 1 proton and 2 neutrons, right? We have 2 neutrons. And then we're going to mash these together, right? We're going to mash these together, and we're going to form a helium nucleus, and we're going to release 1 neutron, right? So when we add all this together, All right, we had all this together. So remember, we have total 2 atomic mass units. One is a proton, one is a neutron. In this one, we have 3 atomic mass units. One is a proton, 2 are neutrons. And then when we add them together, we get 4 atomic mass units. 2 are protons, 2 are neutrons, and then we have this lone neutron here. So that's fusing this together. So we're taking 2 smaller ones, making a bigger piece with a little bit of a fragment. And this is what they look like. All right, so now the next thing to do is understand is that this does require a lot of energy. Now here's an equation you've probably heard a lot of, but really don't understand what's going on, the energy of a nuclear reaction. And then this is Einstein's equation, E equals mc squared. And this is what they call the mass defect. In some nuclear reactions, a small amount of the matter is actually converted into energy, right? Now this kind of goes against that we can't create or destroy matter. But now we're telling you that you can take some of the matter that we said you can't create or destroy and converting it into energy, right? Very small amount. But the energy created in a nuclear reaction is hugely greater than the ordinary chemical reactions. That's why we can get away with, that's why people are looking towards nuclear energy as a source of energy. You don't need a lot. You don't need a lot of material to get a lot of energy out of it. All right, and so E equals mc squared, and then the general equation is, and I just want to show you how big this can be. So let's just say we had, let's going to do a little writing here. So here's my equation, E equals mc squared, right? And let's just say I had 1 kilogram of material, and we're going to convert it all into energy, right? And we have, so my kilogram, and remember it's our meters per second squared. All right, I'll tell you that in a minute. So these are our units when we do the equation, if we do the equation right. And a kilogram meters per second squared, if you can remember, I don't know if you can, is equal to a joule. Right, joule. And so that's a unit of energy, we know that. And so let's just do the simple equation here. C will stand for, remember what C stands for, speed of light is 3 times 10 to the 8th, and I'm going to write it here, meters per second. All right, that's the speed of light. So 3 times 10 to the 8th times 3 times 10 to the 8th. So just write this down here to make it simple. 1 kilogram times 3 times 10 to the 8th. That whole number is squared, and we'll, right? So I'm going to erase some of this other stuff here. Let me erase some of this other stuff here so we get some room to write some information. And so you can already start to see here that if I'm going to square 10 to the 8th, right, that's going to give me 10 to the 16th, right, 10 to the 16th. So let's just write that down right now. It's going to be 10 to the 16th. And I'm also going to square the 3, and that's going to give me 9. So 9 times 10 to the 16th times 1 kilograms, that's the same. And that's all going to equal a joule. So 9 times 10 to the 16th joules results from 1 kilogram being all converted into energy using the Einstein equation of E equals mc squared. That is a huge amount of energy, right? Now you talked about Back to the Future, 1.121 gigawatts, right? That's 10 to the 12th. That's like a bolt of lightning. Somewhere in that, that's how much energy goes through there. So look at this. 1 small kilogram is going to give me 10,000 times the energy equivalent of a bolt of lightning. Quite a bit. So there's a lot of aspects of radioactivity that you deal with every day of your life, and some good, some bad, but a lot of it has been used to better mankind. Carbon-14 is used to date the age of organic materials, so a lot of archaeology, anthropology use this. Uranium-238 is used to determine the age of rock formations. Again, we're back into the study of earth science and stuff like that. Radioactive tracers, they show the path of substance that follow through a body. and they have to have a short half-life, obviously, and travel quickly through the body, but they can illuminate areas where you have cancerous or growth, some type of abnormality cells growth, or they can help you trace the blood pathway of something and see if you have internal bleedings anywhere. Nuclear power, obviously, we all live with some type of nuclear power at one way or the other. Nuclear bombs, they blow stuff up. Not necessarily a good thing for mankind, but the nuclear power and the nuclear bombs are the same thing. It's just one is used to hopefully better mankind, and one is used to not better mankind. They use gamma radiation to fight cancer, and they radiate food to prevent spoilage and things like that. So a lot of the food you eat, meats and stuff like that, are irradiated at low levels of radiation to promote shelf life. Of course, with anything, there's always good and the bad here for nuclear power is that we generate nuclear waste, and nuclear waste is a byproduct that is harmful to the environment and generally remains for thousands of years. So its effect on the environment is long-lasting. There are nuclear accidents, so they have releases of nuclear waste or nuclear products into the environment that can affect humans. Chernobyl was one. They just had the one in Japan, 3 Mile Island back in Pennsylvania in the mid-70s. So you have to be careful with it, but if you're careful with it, you can get a lot of energy out for a little bit of material. So, and that concludes the unit on nuclear energy, nuclear power, nuclear chemistry.